A certain amount of force is required to do that, about 10 newtons here on Earth, because the pull of gravity is about 10 meters per second here. That's little g. I'm going to assume that little g is about 10 throughout this video. So it's 10 newtons of force from the finger to hold up that 10 newton weight force from the 1 kilogram mass. Now here's the famous thing about levers. If you halve the mass but double the distance from the pivot, the finger doesn't feel any difference. The mass now has double the mechanical advantage, but it has half the mass and they cancel out. If you halve the mass but double the distance, the turning force stays the same. That's the thing we know about levers. And so your finger is required to apply the same force as before, about 10 newtons. Your finger cannot tell the difference between the 1 kilogram mass that's the same distance away from the pivot as your finger and the half kilogram mass that's twice the distance away from the pivot as your finger. In fact, you could put the mass end of the lever in a black box and there's nothing you could do with your finger to be able to distinguish between a 1 kilogram mass and a half kilogram mass that's twice as far away. There's no experiment that you could do to figure out which one it was. The finger has the same experience because the force is the same in both scenarios. Okay, so back into space now, and we're going to do the same thing. We're going to move the mass twice as far away and we're going to halve it. That's half a kilogram. And again, the rocket will apply a force of 1 newton over a distance of 1 meter, which of course means that the mass will be pushed over a distance of 2 meters because that side of the lever is twice as long. And so the mass gains some kinetic energy. Now, the rocket can't distinguish between these two situations. The experience of the rocket should be the same in both cases, as we know from the levers on Earth. The reaction force of the rocket will be the same, and so the acceleration of the rocket will be the same. And so the rate at which the lever rotates around the pivot will be the same, like this. Now this end of this lever is travelling twice as fast as this end of this lever because it's twice as far from the pivot. So after the engines turn off, the half kilogram mass will be travelling at twice the speed of the 1 kilogram mass. So how does that affect its kinetic energy? What happens to the kinetic energy of something when you halve the mass and double the speed? Well, let's take a look at the equation for kinetic energy. You've got that v squared term in there. Let's write that out as v times v. So we've got a half mvv. And remember, we're halving the mass and doubling the velocity. So the kinetic energy is halved, then doubled again. Now, if you halve something, then double it, that cancels out, and we're just left with that final doubling. So instead of 1 joule, it's double that. It's 2 joules. And if you want to use actual values, we can do that, because if you remember earlier, we got a value for the velocity of the 1 kilogram mass of √2, but of course we're doubling that, so it's 2 √2. Squaring that gives you 8. The mass is half, so we divide by 2, and then half again because the equation for kinetic energy has a half in it. That gives you 2 joules. But remember, the rockets are having an identical experience. 1 newton over 1 meter is 1 joule. So I've just shown that we can put 1 joule of energy into a lever and get 2 joules of energy back out. So that means one of two things. Either free energy technology is real and the government is suppressing it, or Steve doesn't understand levers. Or to be more precise, one of those logical steps, let's put it in scare quotes, one of those logical steps was wrong.